Our next presentation presenters are Kelly Damalou and Matt Commens from Ansys. Kelly is going to start where she's the product manager for the semiconductor on chip electromagnetic simulation portfolio at Ansys, and over 20 years of experience working closely with leading semiconductor companies. And Matt Commens is the senior manager of the electronics product management team at Ansys, and he's been there for over 20 years, and he's responsible for the strategic product direction of Ansys HFSS, and is a recognized expert in computational electromagnetics. So Kelly, all yours.
Thank you very much. So very happy to be here today. And we're going to talk about signal integrity analysis at the dawn of the interposer era. So I will start my presentation by briefly talking about heterogeneous integration, and John covered a lot of that, of course. It's fundamental components, 3D ICs, chiplets, and interposers. And as the scope of this conference is to go beyond just chips, this presentation will focus on silicon interposers and the signal integrity sign of challenges of high-speed buses that travel in the interposers. To address these challenges, Ansys offers solutions that approach the problem from an IC perspective and from a system perspective. And both of these will let users sign off multi-die architectures with the known Ansys golden confidence. So let me jump to my next slide and talk about the trends that have been shaping the IC design industry during the recent years. So to achieve gains in power, performance, area, and cost, 3D IC architectures are pushing electronics design to new limits. Silicon integration technology and associated devices have undergone an impressive evolution over the last several decades, and their development encourages technological advancement in applications like high-performance computing, artificial intelligence, processors, central processing units, CPUs, and GPU chips, graphical processing units. These applications that require ultra-high performance and low power, also covering 5G, 6G telecommunications, networking, all the high-performance computing that I mentioned. And besides that, the automotive industry that is in constant pursuit of fully autonomous vehicles, they're all pushing the boundaries of IC design. And even though SoCs today pack an incredible amount of functionality into a single die with hundreds of millions of gates and very high operating speeds, there are many challenges and concerns that drive the industry towards alternative architectures where multiple die are placed into a single package. And 3D IC architectures can integrate those multiple die, or chiplets as we call them, as we say, such as logic chips, chiplets, memory, RF into this single design. Two important aspects of heterogeneous integration are the substrate technologies and the chiplet-to-chiplet communication interfaces. Substrate technologies mainly fall into two categories: silicon interposers like CoWoS and organic interposers like InFO. Physical communication interfaces can be serial, where SerDes blocks take care of the conversion of parallel data input to serial data output, and vice versa. So here there's an example of an HBM memory and SerDes design, and I should click here. And these parallel interfaces can be HBM2, HBM3, or UCIe, newest protocol, and they are excellent in enabling high bandwidth communication between the memory and the CPU or the GPUs. Stacked 3D IC arrangements and side-by-side 2.5D arrangements lay out help designers surpass the limitations of Moore's law by making it feasible to achieve performance gains at the individual chip or practically chiplet level. Significant performance and cost gains can be made with heterogeneous integration by using the most appropriate process technology for each chiplet in a 2.5D or 3D IC assembly. And an important feature of multi-die 2.5D IC assemblies is the interposer, which carries the signal and the power interconnect between chiplets. Interposers are most typically implemented as a large silicon chip with interconnect feature sizes based on mature process nodes like 65 nanometers. And high-speed digital buses transfer information between chiplets, including high-performance graphics accelerators, network controllers, I/O blocks, machine learning chips, SoCs, high-speed memories, whatever. So all sorts of chiplets. Heterogeneous integration implies the addition of analog signals to custom chiplets like wireless communication and sensors. In order to achieve the optimal power performance area and cost trade-off, engineers need to start the exploration of alternative architectures earlier than with monolithic SoCs. In the design cycle that they traditionally use, there are lots of new multiphysics effects that need to be considered. Performance analysis should also start as early as possible and continue throughout the process, the design process. Thermal and structural integrity become very critical parameters for the decision-making process, how they decide to split the functionality between different chiplets. And therefore, the design flow needs to be radically redefined in order to cover the engineering requirements that emerge with 2.5D and 3D IC architectures. The 3D IC system exploration and floor planning should be done in parallel with early stage analysis of signal power, thermal, and mechanical integrity. Designers have to deal with routability decisions that involve the interposer and TSVs, and also manage the clock skew across the design levels. The sign-off phase should include the accurate modeling of TSVs and the interposer, as well as detailed analysis of the different physics aspects: signal integrity, power integrity, thermal integrity, and mechanical. Mostly all of those steps of the design process should be revised to take into account the particularities of the 3D IC architecture. And if you're a designer, you already know by experience, or you can guess if you're not a designer, that this new approach for going from monolithic chips to 3D ICs would require new tools and methodologies to be adopted in the design flow. 3D ICs should be built on a common database that would practically streamline the exchange of data and analysis information. It will be able to support a variety of data formats. It will be fast, efficient, and scalable. So today, with all sorts of disparate tools and databases, engineers struggle to get their products out of the door on time with the required level of confidence. So for sure, a common workflow would help design teams that work today in silos to collaborate more closely and achieve better results. The benefits of 2.5D ICs come with trade-offs, and 3D ICs, of course, including the need to confront new and exacerbated physics. And those physics were not something that monolithic chip designers had to worry much about. They were able to model them and make up for them with some margins. Now in 2.5Ds and 3D ICs, they are much more critical. And one of the most critical of these new concerns is high accuracy signal integrity sign-off for the interconnect on silicon interposers. Signal integrity is, of course, not a new problem. It is a standard part of analyzing any chip or printed circuit board. So what really makes it so different in the case of silicon interposers? The answer is the unprecedented combination of silicon density and very high data rates. New communication protocols push frequencies constantly higher. The complexity of the layout increases with every new process node, and so does the risk of failure, as legacy design methodologies where components are designed and verified separately leave significant room for error. For the accurate signal integrity sign-off of high-speed interconnect, the buses that connect the various dies should be extracted with electromagnetic accuracy in the presence of the power delivery network and ground networks in order to account for the coupling phenomena between the power, the ground, and the signals. Traditional methods that accounted only for the RC parasitics of a few signals, ignoring the presence of the power and the ground networks altogether, can lead to enormous errors and design respins that are too costly and can sum up to many hundreds of thousands of dollars, delaying in parallel the time to market and the time to profit for any product. Traditional PCB tools don't have the capacity to analyze interposers with many thousands of or even millions of interconnections. While traditional IC tools for signal integrity do not take into account the novel physics effects of large-scale structures like through silicon vias or high-speed signals running over multiple millimeters, several orders of magnitude longer than any on-chip interconnect. For signal integrity experts that validate silicon interposers through an IC design flow, Ansys has a powerful workflow that we call RaptorH that combines two golden electromagnetic solvers, the full-wave golden HFSS and the silicon-optimized RaptorX. This die-centric workflow seamlessly integrates in Cadence Virtuoso and Synopsys Custom Compiler. It uses an open access, it reads open access databases or GDS files as inputs, and also reads Foundry ITF or IRCX tech files, even encrypted ones, streamlining thus the workflow from layout to signal integrity sign-off. Ansys RaptorH workflow automates layout simplifications in memory and thus leaves your golden layout untouched. It also seamlessly interfaces with the Ansys system level platform, the Ansys Electronics desktop, for full system analysis and sign-off. RaptorX, the silicon optimized solver that runs within RaptorH, it has been certified by TSMC and Samsung for its accuracy in the signal integrity analysis of 2.5D and 3D IC technologies. And Ansys customers are able to sign off more than 100 signals in the presence of extremely complex perforated power and ground planes and outperform competition in accuracy, capacity, and speed during every benchmark where we have engaged. Here you can see some indicative results from the certification of the RaptorX solver by TSMC. And as you can see, the correlation of RaptorX outputs versus the TSMC golden reference for insertion and return loss for this silicon interposer you can see here on the left, the correlation is excellent. There are two important features of silicon interposers that significantly stress traditional signal integrity solutions. So one of them is through silicon vias, also known as TSVs in short, that provide direct connections from top metal to the backside metal layers. Compared to a wire-bonded system in package, TSVs offer reduced RLC parasitics, better performance, more power savings, and a denser implementation. Silicon interposers can have thousands or hundreds of thousands of TSVs actually. While traditional methodologies of signal integrity can only extract a handful of TSVs, which are then cascaded in circuit simulation to have a full system solution, the Ansys solution powered by RaptorX can model thousands of TSVs analytically, taking into account the coupling between them in order to accurately assess the performance of the high-speed buses. The other important feature of silicon interposers is the presence of thousands of ultra-high density capacitors, what you see in the literature called iCAPS or deep trench capacitors, DTCs. They are widely popular building blocks of the power management network of the interposer. And from a modeling perspective, they are treated similarly to TSVs. Usually designers have a trusted model for one of their capacitors, and they cascade that during circuit simulation. So again, this leaves significant room for error in the design of power delivery networks. And RaptorX, which is the Ansys silicon optimized electromagnetic solver, can give the capacity and the speed to solve all of the interposer capacitors of the design at once with the highest accuracy. So I will use this example to emphasize the capacity and the speed of RaptorX that allowed us to model this interposer that is 6 millimeters long and has been flooded by dense dummy tiling on metal 1. So thousands of floating metals on M1 going for along the interposer for 6 millimeters. You can imagine what kind of dense metallization that is. And you see a small sample of that here. Maybe I should turn on my pointer. So here's a small sample of the interposer flooded by these metal 1 dummy tiles. RaptorX produced an electromagnetic model for this interposer that had 3 conductor layers, the patterned ground shield, and all the floating metals in less than 30 minutes. And it used 56 gigabytes of RAM on 40 CPUs, which is literally breathtaking for anyone who has dared to solve a similar problem. And I have another test case following up. Another interposer design, an HBM3 bus with 48 signals built on a silicon interposer. I will use this example to demonstrate the accuracy of the RaptorX solver. So the HBM3 bus was several millimeters long, 5.2 millimeters by 0.04 millimeters. And the electromagnetic simulation covered DC up to 20 gigahertz frequency range. You can see here some correlations for the transmission and the reflection of 2 different nets between RaptorX and the HFSS golden reference. And as you can see in these plots, the correlation is excellent. Insertion loss on the left and return loss on the right, with the HFSS being the red curve and RaptorX being the green curve. They have excellent correlation. Equally successful was the correlation of the far and the near end crosstalk. So here's the far end crosstalk and here's the near end crosstalk. Again, HFSS is the red curve and RaptorX is the green curve. And again, you can see that RaptorX delivers the same level of a golden accuracy as HFSS. And to close this proof point, these are the output waveforms. The output waveforms from HFSS and RaptorX, and the eye diagram, you can hardly distinguish between the plots of HFSS and RaptorX, which again testifies to the golden accuracy of the delivered results between the 2 different Ansys electromagnetic solvers. And with that, I will let the floor now to Matt, who will present the system-centric approach for signal integrity analysis. So Matt, I will advance the slides for you.
All right, thanks, Kelly. Yeah, so I'll carry us through to the end with a discussion on tackling system-level design with HFSS. The highly performant RaptorX solver for on-chip extraction, you can extract very, very fast results, and as Kelly demonstrated, with quite good agreement between HFSS. But the days of solving a few nets on a package alone and then building in design rules with buffer to assemble a system are essentially going to be behind us, if not already, because engineers are being driven to create more and more highly performant systems and designs. So next slide, Kelly. So just a quick review of HFSS. HFSS is built on a technique called the finite element method. This is a technique where you discretize the entire geometry, conductors and dielectrics, including the surrounding volume, and then leverage that discretization using a technique called adaptive meshing to essentially use Maxwell's equations to guide how the mesh will be generated on the CAD. And this really removes one of the significant burdens from someone trying to leverage simulation, not having to figure out exactly how to generate the mesh in the most accurate and combined with efficient fashion. And so what you're looking at here is a mesh adapting on a spiral inductor. On the right-hand side, you see the Q curve of that inductor converging to its final result. So this is what provides very, very reliable solutions that you can really make some accurate judgments and design decisions on your device. Next slide. So specific to interposers, as Kelly's already mentioned, the CAD can be extraordinarily complex. That's probably one of the most significant differences that we might see in terms of this newest packaging technology versus, say, organic packaging from 10 years ago or so. And so they're challenging. To achieve the discretization takes a lot of mesh elements. Meshing alone can be challenging, but we can tackle these fairly complex interposer designs. Here's an example of interposer design that includes the through silicon vias on the bottom layers. Next slide, please. Just take a quick snapshot of some of the simulation performance for this particular design, and just some more details on how you set up the simulations. If you're familiar with HFSS, these settings will be very familiar to you. But one of the key things you take away from this is, we're discretizing the entire geometry, not just the conductors, the dielectrics as well as the surrounding air volume, to capture the entire electromagnetic effects in and about the device. Next slide. And one of the key things you can take away from analysis with HFSS that, oftentimes we don't see people leveraging this output, but one of the nice features you can get from a simulation like this is you can actually visualize electromagnetic fields in and around your device. More commonly, people might be looking at SYZ parameters, looking at system metrics to determine performance. But if you might observe an issue at a particular frequency, you can use this functionality to really give you a type of insight that, quite honestly, is really impossible to achieve in a lab. And that's kind of one of the big advantages you have with simulation over test and measurement, is this level of physics insight that you can gather. Next slide. So real quickly, we're going to talk about interposer optimization. We're going to start out by just discussing two tools in particular. One is HFSS 3D layout, and then the 3D layout is essentially a dedicated workflow for the HFSS solver for IC package and PCB designs. We're showing an example here of a flex PCB design with the full system simulation run, the surrounding electric fields on the structure. Again, employs the 3D finite element method, uses adaptive meshing, has very powerful technologies like multi-technology stacking up. You can stack IC on package on PCB very easily. One of the other key features of this workflow is it's very easy to define parameters, whether they are parameters for geometry, CAD, via spacing, for example, or even looking at material properties. The workflow itself has many EM solvers. Again, we'll focus on HFSS here, but it also has our PCB solver, SI Wave, and a planar method of moment solver as well. And finally, it's all coupled together in one desktop with our next in-time domain circuit simulation. Next slide, please. The other tool to this discussion on optimization for interposers and IC is optiSLang. And it really highlights the power of variational analysis. And that's really what we're going to get to here in a second. Being able to derive parametric designs easily, allow you to create design rules up front or validate designs on the back, optimize and validate designs on the back end, can be a really powerful addition to your workflow. So rather than just using simulation for final validation, you can use it throughout your design flow. So with parametric study and instances, we can leverage different optimization technologies. There's even machine learning capability within optiSLang to leverage the parametric plus optimization technique. And you can do, address topics like robust design optimization, uncertainty quantification, and design for Six Sigma. So essentially, optiSLang is essentially a system driving tool that will leverage the HFSS workflow in 3D layout to gather data and then help you optimize your system. Next slide. So what we're looking at here is the parameterization, some examples of the parameterizations that are available in 3D layout. You can parameterize pretty much any aspect of your design, trace spacings, via diameters. You can also look at, what we're not looking at here is you can even look at material properties in case you want to do yield studies, for example. But the key takeaway from here, with all these different parameters available to you, you can do some interesting different sets of analysis with the combination of optiSLang and HFSS 3D layout. So next slide. So with optiSLang, you can build up things like a response surface to your design, take a finite sample of design points, extract the data. You can leverage HPC or even cloud technology to extract these data points quickly. optiSLang builds up a response surface, and upon that response surface, you can do optimization, including with machine learning techniques. And one of the more valuable things you can get out of such a study is really understand which of your design factors are going to have the biggest impact. In this case here, the design input interposer VSS width clearly has the biggest impact on the overall performance of the design. So next slide. And with this capability, and on top of that, optimization routines, you can take your, in this case, an interposer design and improve your return loss by 10 dB in this particular example. So again, what's happening here is the design is created, it's parameterized, it's fed into optiSLang to determine which parameters have the biggest impact, and then automatically optimize for tuning and performance. Next slide. Okay, so let's talk about system now. So interposer on package on PCB. This is not unheard of today. 5, 6, 7 years ago, it would almost be unheard of to be combining both together. But again, this is where heterogeneous design is leading us, is to these requirements to be able to do system design, to do IC on package on PCB, even in some cases, including surface mount components in the analysis, because the drive towards very performant designs with the tightest possible design margins are really a critical factor into achieving the performance specs that people are after. So here you see a number of examples of different parameters can be varied via spacings, via locations, trace widths, but not just on a single part of a component, but across the entire system. So looking at routing, pad sizes, trace width, etc. So next slide. And again, on the system, you can then use optimization routines with optiSLang to, again, understand which are your most important design parameters to consider, and do full system analysis and optimize, in this case, insertion loss for this system design. Next slide. And this can even be taken out to the system level output, such as an eye diagram. So here we're looking at a PAM4 output. This is actually using the NextSim time domain circuit simulator coupled to the HFSS results for the system, and showing your optimized system eye diagram output at the end of the simulation flow. Next slide. So lastly, with this combination of the very performant on-chip extraction tool, RaptorX, help you design your IC-based part of your design very quickly, brought together within the HFSS 3D layout workflow. Again, mentioned earlier, the RaptorX engine and the HFSS engine are coupled through a technology called HFSS layout components. These can be stacked together, built up in a system, and allow you to do a final system sign-off with a combination of optimization and HFSS solutions. And one last thing to mention, one of the big breakthroughs that's come recently is a technology called Mesh Fusion. Without getting into details about what that is, one of the big breakthroughs that provides is what's seen here is the ability to mesh and solve over scale. So when we say over scale, it's like from the PCB up through the package up onto the IC. You could be moving over many orders of magnitude in design feature size, and that's a very, very challenging meshing problem, and it is achievable today with Mesh Fusion. So with that, we'll wrap up our discussion on signal integrity analysis in the new interposer era, and open up for some questions.
Thank you, Matt. So, first thing that really comes to mind, people talk about signal integrity and power integrity separately. I mean, in the new era, is it all one thing now? And
I would say no. Kelly did mention it earlier. It is actually very important now to have them together. That just makes the problem that much more difficult. But it is important. You have to have both things under consideration, both output, signal, and power integrity under consideration. Kelly, I don't know if you want to make any comment towards this.
No, that's practically the idea. We have to keep both things, both aspects in track, and one affects the other. So we need to constantly monitor and make sure that the impact of one to the other is taken into account for the final sign-off. So it's much more complex than for monolithic ICs, and the EDA technology needs to follow.
And Matt, you were touching upon it being in, let's say, multiple domains, like the printed circuit board design domain is different than the interposer, for example. Printed circuit boards are typically designed, or the output of a printed circuit board design system is Gerber, and interposer may be done with GDS2. So does the tool, can the tool aggregate multiple designs using different data sources?
Yes, yeah, absolutely, and that's one of the great virtues of the hierarchical structure to the workflow. So you can bring in a IC part of your design with GDS workflow. Your interposer design might be done with a packaging tool. We have links to all the common packaging tools. And again, your PCB could be done in one of the common PCB design tools, or could come through with, say, a IPC 2581 format. So that's one of the great virtues of this flow, is we can couple to pretty much into any design flow, build up the individual subcomponents, and then assemble them into a hierarchy and do a full system analysis from there.
And then your discussion about the adaptive meshing is that you mesh at the right level for each scale so that you don't have to overcompute. Is that
right? Exactly. Yeah. Thanks. Yeah. It's literally you're letting Maxwell's equations tell you where to put the fine, dense elements where you need the high accuracy for high field concentrations or gradients. And then other parts of design where there's just not much going on, you can leave a coarser mesh and save on compute resources and achieve a higher efficiency.
Mm-hmm, mm-hmm. And did you talked about RaptorX, but was there also another product you mentioned, RaptorH, or what's the difference?
Yeah, that's a good question. So the really RaptorX you could speak of as being a design flow as well as a solver engine, and this is the solver engine we talk about being highly performant on chip. The RaptorH is essentially, think of it as the RaptorX flow plus engine along with the HFSS solver engine plugged into the background. It's really there for sort of a different persona than the system engineer. It's really for someone who's very IC centric in their workflow, but they still want to leverage the HFSS solver engine along with the RaptorX solver engine.
Okay, got it. Oh, good. I don't see any other questions, so I want to thank both of you. So thank you, and for the audience, there are polls that I put up after every presenter, so if you could take a minute to give Matt and Kelly some feedback, it'd be greatly appreciated. Thank you.
Thanks, Ira.
Then once again, I would like to thank our lead sponsor, Advantest, rated as the #1 supplier of semiconductor equipment in 2022. And our other sponsors, Amcor and Cadence, their sponsorship has made this event possible and free of charge. So when you have an opportunity, please thank them. And I thank all of you for joining us today. And we look forward to seeing you tomorrow. Have a good rest of your day.